6.3 Numerical Model in Biomechanics. Biomechanics is the mechanics of the body in relation to sport. This includes the force applied on and by the body and the outcome of those forces. This study can be used to decrease the risk of injury or enhance performance. Within this, biomechanics breaks down into kinematics and kinetics. Kinematics is the study of the motion of a body or object. Within this is linear motion, angular motion, and general motion. Within linear motion is rectilinear motion and curvilinear motion. Linear motion is motion where all the parts of the system move in the same direction and in the same speed. So this probably wouldn't include something like a sprint, because your arms are moving at different speeds to the rest of your body. The whole system isn't working as one unit. Specifically within this, rectilinear motion is motion that's on a straight line, and curvilinear motion is obviously on a curved line. This would again mean that all parts of that system are moving in the same direction and same speed, but this might be curved or straight. Angular motion is when this system moves around an axis. So all parts move around the same angle, same direction, same speed. So it's similar to the first, but this is around an axis this time. And finally, general motion is a combination of both linear and angular. It's most common, really, out of all of the types of motion. An example of linear motion is a ball rolling across a court. An example of angular motion might be the movement around a bar in gymnastics, the bar being the axis in this case. And an example of general motion would be your movement in a 100-meter sprint. This is because, like previously mentioned, there's the angular motion of your arm movement perhaps, or your shoulder move, like the movement at your shoulder around that axis there, and it combines the linear motion of perhaps like your chest moving forward at that same speed as you run along. Within biomechanics, we also have kinetics. Kinetics is the movement of an object or body in relation to forces. So within kinetics, there is angular kinetics, there is linear kinetics, which subdivides into rectilinear kinetics and curvilinear kinetics. You can see that these are similar to kinematics in the sense that there's linear, rectilinear, curvilinear, and angular, but there isn't general. It's almost the force form of kinematics. For example, angular kinematics relates to angular kinetics because it has that link to levers. Linear kinetics examples are force, gravity, mass, and weight, whereas angular kinetics are moments and levers. So what actually is a numerical model? A numerical model is a mathematical form of representing sports performance through the use of numbers and units, of course. It's used to analyse performances to ensure safety or advancement in performance, and is often carried out on software on computers. This is of course to make the analysis easier, as the software enhances the speed and detail of the process. Methods of research to create a numerical model include textbooks, YouTube videos, academic articles, internet sites, and even research on elite performers. Within this though, I personally would look to academic articles and elite performers, as that's probably more reliable than YouTube videos and internet sites where false information could be found. There are strengths and weaknesses of the use of a numerical model. So strengths might include the fact that because it's numerical, it's easily measured, so you can compare things very easily with each other, whereas just units and numbers, it's very easy to compare those two things. And therefore this kind of enables you to present this information in tables and graphs, which might be easier for some people to read and more easily presented. Whereas some weaknesses of the numerical model include that it can be hard to adjust your technique or things specific to technique, I'd say, based off of numbers. So perhaps a technical model might be more beneficial in that sense. I'd also say that fast-paced sports can be difficult to follow players' movement. So if you were perhaps filming for a numerical model, you'd have to take into account the pace of certain movements and certain sports, which can make that filming process quite difficult. Now, within this biomechanics and motion, there's obviously linear motion, and within that there are scalars and vectors. So scalars are quantities that have only magnitude, whereas vectors are quantities that have both magnitude and direction. Some examples of scalar quantities are distance, speed, mass, and inertia. And some examples of vector quantities are displacement, velocity, acceleration, deceleration, weight, and momentum. And we will see how these differ now through some examples. So here we have speed and velocity. So speed is a scalar quantity as it only has magnitude, whereas velocity is a vector quantity as it has both magnitude and direction. An example of where speed is applied in basketball, for example, is the ball travels at 2 meters per second when a player makes a pass. That would be speed. And an example of where velocity is applied in basketball is the ball travels at 2 meters per second east when making a pass. Can you see that there's the application of direction here by the use of the word east? Another example is distance and displacement. So distance is a scalar quantity because it only has magnitude, and displacement is a vector quantity as it has both magnitude and direction. So again, applying this to basketball, if a performer takes a shot from 3 meters away and the ball rebounds off the backboard and returns to the player, the displacement of the ball is 0 meters because it's gone to that backboard and come back to the player. So it's come back to its original position, so the displacement is 0. Whereas the distance the ball has travelled is 6 meters because it's travelled that initial 3 meters to the backboard and then that 3 meters backwards to the player. So you can see the difference in displacement and distance here because displacement involves direction. So in this case, the ball has travelled one direction and then come back the opposite direction, so it counteracts and creates that displacement of 0. Whereas the distance has no direction, so it takes into account both of the journeys to create that 6 meters. So comparing the two here, you've got a distance time graph and a velocity time graph. So we're looking at both the examples we've had so far, one being scalar, distance, and one being vector, velocity. So here you can see examples of how this graph would display that time and distance, okay? So you'd have perhaps distance here, as you can see here, and time here. So this shows a constant velocity, which is a straight diagonal across, because as you move 1 second, you're going up 1 meter perhaps. In this case, it would be different. So here now, on the velocity time graph, you can see that this diagonal line that we saw in the distance time graph actually represents acceleration, and it's this straight line here that represents this constant speed, this constant velocity. Moving on swiftly to acceleration then. So acceleration is the rate at which a body changes its velocity. Therefore it is a vector quantity, so it has both magnitude and direction. So the measure of this is meters per second squared. An example of acceleration in basketball again is starting from a stationary position and then running left to get into space quickly and receive a pass. Noticing the left is that direction that makes it a vector. Another sporting example would be a 100-meter sprint start. As you accelerate forward at the start, the performer would have a positive acceleration at the start of the 100-meter sprint, but a negative acceleration after you pass that finish line. Moving on to forces then, so back onto the kinetics side of things, let's focus on inertia. So inertia is the ideology that an object remains at rest or uniform motion until an external force is applied. This can also be explained as the reluctance of an object to change. This might be in golf when the ball remains at rest until you hit it with the club. Obviously, the external force must be larger than the object's inertia for a change in motion. If you had a larger inertia, a larger resistance to that force that you're applying, that external force, then that object's not going to go anywhere. Now let's look at the effects of force. So you have 5 effects of force. One is causing an object to change from resting to moving. So for example, a chest pass in basketball would require a force for it to change from resting to moving. Another is changing the direction of an object. For example, an interception in basketball causes the ball to change direction. In addition to this, force can cause an object to accelerate. For example, yet again the chest pass would be acceleration of the ball. It's moving from resting and increasing in that velocity in a specific direction. Force can also do the opposite and cause deceleration. And finally, force can cause the object to change its shape. So for example, bouncing a basketball when dribbling changes the shape of the ball, because as the ball makes contact with the floor, that force from the ground alters the ball's shape. So now we have Newton's laws of motion. So Newton's first law states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. So this is that inertia principle that we've previously mentioned. Newton's second law is force equals mass times acceleration, to put it into simple terms. So that force will increase if the mass or acceleration does. So an object with a larger mass will require a larger force to accelerate. For example, if you apply the same force on 2 different sized basketballs, the smaller ball will accelerate faster as it has a smaller mass. Each action has an equal and opposite reaction. So this is the third law now. For example, when you bounce a basketball, the action or the force of the ball hitting the ground is equaled by the force of the ground. Okay? So that force you're applying on the ball to push it into the ground is equaled by the force from the ground. That the ground has a upwards force on the ball and it's equal. This causes the ball to bounce back up. So that is how you dribble the basketball.